Greetings and salutations, everybody. This is Jacob. So, how do we go about solving this problem? It seems complicated. Well, my friends, it actually is. But the journey of 1,000 miles always starts with one step, as they say. So let's get this show on the road, shall we? Since, as we said, the instantaneous velocity of boat A is always pointed towards boat B, then the tangent to the pursuit curve always passes through point Q, correct? So by using the slope of a line formula, we have dy over dx equals y minus beta times t over x minus 1. Since boat A is traveling at a speed alpha, and after t hours it will have traveled a times t. This distance is also the length of the pursuit curve from 0.0 to x comma y. So using the formula of the arc length of a curve from calculus, we have alpha times t equals the definite integral from 0 to x with the square root of 1 plus the derivative of y squared du. So we solve for t in the previous equation, and we plug that in the second equation, and we get y minus x minus 1 times dy dx over beta equals 1 over alpha times the definite integral from 0 to x with the square root of 1 plus the derivative of u squared du. So now we differentiate both sides with respect to x, and we get y plus dy dx minus x dy dx prime equals beta over alpha times the square root of 1 plus dy dx squared, which is d squared y over dx squared, which is a second derivative of the function of y, minus x d squared y over dx squared equals beta over alpha times the square root of 1 plus dy dx squared, which is x minus 1, d squared y over dx squared equals minus beta over alpha times the square root of 1 plus dy dx squared. We change the variables, we call dy dx equals w, and now we have x minus 1 dw dx equals minus beta over alpha times the square root of 1 plus w squared, which is a first order linear differential equation. And we use the method of separation of variables to solve this. So we separate the variables, and we have 1 over the square root 1 plus w squared dw equals negative beta over alpha times 1 over x minus 1 dx. Now we integrate both sides, and we have integral 1 over square root of 1 plus w squared dw equals minus beta over alpha integral 1 over x minus 1 dx. The right side is easy. It's just a natural logarithm of x minus 1 plus c. But what about the left side? How the heck do we integrate this expression here? Well, some clever trigonometric substitutions are going to be needed here, my friends, unfortunately. So let's call w equals tangent of u. So u equals arctangent of w, and dw du equals tangent u prime, which is secant squared u, and dw equals secant squared u du. And so we plug these into the integral, and we have integral secant u over square root of tangent squared of u plus 1 du. There's a formula that relates tangent u to secant u, which is tangent squared u plus 1 equals secant squared u. And so we plug that into the integral, and we get secant squared u over square root of secant squared u du, which is just integral secant u du after simplifying. So now we multiply secant u with tangent u plus secant u over tangent u plus secant u. And I'll show you why we do this. So we expand, and we get secant u times tangent u plus secant squared u over tangent u plus secant u du. Now we make a second substitution. Yes, I know, my friends. Please bear with me a little longer. This torturous integral will be over in no time. We'll call v equals tangent u plus secant u. So dv du equals the derivative of tangent u plus secant u. And the derivative of tangent u is secant squared u. And the derivative of secant u is secant u times tangent u. And so the derivative of this whole thing is secant u times tangent u plus secant squared u. And we have du equals 1 over secant u tangent u plus secant u squared times dv. And so we make substitutions in our current integral, and it becomes this expression here. And as you see here, magically, the numerator and the denominator cancel out. And we end up with something that looks integrable, which is 1 over v dv. Hallelujah. That's why we went through this whole song and dance with these substitutions, my friends. And so we know the antiderivative of 1 over v. That's easy. It's just natural logarithm of absolute value of v plus the constant of integration, c. Now we substitute back the variables. and we get natural logarithm of the absolute value of tangent u plus secant u. Now we said it earlier that tangent u is just w, but what is secant u? U is arctangent w, as we said earlier. Now we have natural logarithm of w plus secant of arctangent of w. So how the heck do we find secant of arctangent of w? This is the final birth pain, my friends. And then the baby will be out. We'll be over with this torturous integral in no time. So we know the trigonometric identity from earlier. Let's say tangent of y equals w. So now we have 1 plus w squared secant squared y. Since tangent y equals w, then we have y equals arctangent of w. So it becomes secant squared y equals secant squared arctangent of w. And that's 1 plus w squared. So secant arctangent of w is just the square root of 1 plus w squared. So finally we integrated this tortuous integral, which is a natural logarithm of absolute value of square root of 1 plus w squared plus w. So now we have this expression here, as you see here. This x minus 1, we prefer to write this as 1 minus x, and I'll tell you why. Because of the nature of the pursuit curve, boat A is never going to exceed x equals 1. So we want this expression x minus 1 to always be positive. It's only going to be always positive if we write it as 1 minus x. So now we raise both sides by e, and we have this expression here, which is the square root of 1 plus w squared plus w equals e to the power of ln of the absolute value of 1 minus x to the power of minus beta over alpha times e to the c. And e to the c is just another random constant. We'll just call it c, just like before. And e to the power of ln of the absolute value of 1 minus x is just 1 minus x. So now we have square root of 1 plus w squared plus w equals c times 1 minus x to the power of minus beta over alpha. Makes sense so far? Okay, now we solve for w. We square both sides, and we do the calculations and all the algebraic operations, and we end up with this expression here. So now we plug in the initial conditions in order to find c. At x equals 0, we have w equals dy dx equals 0. So we have 0 equals 1/2 times c times 1 to the power of minus beta over alpha minus 1 to the power of beta over alpha over c. We do the calculations, and we end up with c is equal to plus or minus 1. So how do we know which one is the solution? Notice that the tangent to the pursuit curve always has to be positive because of the nature of the curve. So this expression here has to be positive. Notice that the base of these powers is always below 1. And since the base is always below 1, then 1 minus x to the power of beta over alpha is always below 1. 1 over 1 minus x to the power of beta over alpha is always above 1, since when you divide 1 by a number below 1, the division will always be above 1. So in order for this expression to always be positive, then c has to equal 1 instead of negative 1. Make sense? So now we've found c, and we have this expression here, as you see here. So there's one more step to find the pursuit curve. We said earlier that w equals dy dx. So we have to integrate both sides. Luckily, this is easy. Using the power rule of integration, we get this expression here, as you see here. So we have one more constant of integration to find. We just plug in the initial conditions like we did earlier. We have y equals 0 and x equals 0 when t equals 0. We do the calculations, all the algebraic operations, and we end up with c equals beta times alpha over alpha squared minus beta squared. And that's your constant of integration. So now we finally have the pursuit curve in full, as you see here. One of the questions answered. 1 down, 2 to go, my friends. So now we have to answer the question, when do these two boats meet? They meet at x equals 1, obviously. So we plug that into the pursuit curve and we get this expression here. And the first part of the equation is just 0. And we get y equals alpha times beta over alpha squared minus beta squared. So we equate the two y's of the two boats and we get alpha times beta over alpha squared minus beta squared equals beta times t. So t equals alpha over alpha squared minus beta squared. So after alpha over alpha squared minus beta squared hours, boat A will catch boat B at the point 1 comma alpha times beta over alpha squared minus beta squared. And that's your answer. So 2 down, 1 to go, my friends. And we're done with this problem. The more interesting question, the $1 million question. The two speeds are equal, and can boat A catch boat B? Notice when alpha equals beta and the pursuit curve changes. Let's go back for a minute to this equation. Since beta equals alpha, now we have w equals 1 over 2 times 1 minus x to the power of minus 1 minus x. And we integrate both sides like we did before, and we get this expression here, as you see here. So boat A will reach boat B only if x equals 1. So we plug that in the equation, and it becomes y equals negative 1 over 2 times ln of 0 plus 1 over 2 times 1 squared over 2 minus 1 plus c. But ln of 0 is negative infinity. So minus 1 over 2 times ln of 0 is infinity. So boat A has to travel an infinite amount in order to reach x equals 1. So boat A will never reach boat B if their speeds are equal. And that's your answer. Wow. Just wow, you guys. What a problem. All right, guys. I'm sick of this complexity. I won't be posting another differential equations problem for the next 30 videos or so. Jokes aside, this was a pretty interesting problem. I really wanted to do something with pursuit curves, but I severely underestimated the complexity of these problems. Nevertheless, I didn't want to tuck my tail between my legs and do an easier problem, you know? So I gritted my teeth and suffered through this, and you have this video here. Because if you don't torture yourself a little bit, then you can't expand your abilities, my friends. There will be no tucking the tail between our legs on this channel, my friends. We do the problems we want to do and when we want to do them, regardless of the difficulty. Whatever doesn't kill us makes us stronger, as they say. So you know the drill, my friends. Destroy those buttons like there's no tomorrow. The like button, the subscribe button, the notification bell. Comment down below what you think if you found this difficult. Well, I know you found this difficult. This problem was no joke. I promise the next differential equation problem will be easier than this. More goodies on the way, my friends. Logic, lateral thinking, algebra, geometry, probability, combinatorics, set theory, chess, differential equations, physics, calculus will be the main areas of focus on this channel. Stay strong, my friends. God bless you all, and I'll see you in the next video. Bye-bye.